Alright, what we want to address here in this video is some stoichiometry and limiting and excess reactants. So there's a lot of different ways that these questions can be asked, but I've presented it here in such a way that I've seen it pretty commonly asked, and then included several things here that I think that you may be asked to do. First, you need to make sure that if you're not given a chemical equation, that you write and balance a chemical equation. Sometimes you're given a chemical equation, but it's not balanced. No matter what, you need to make sure that you start with a balanced chemical equation for the reaction. In this case, magnesium oxide is formed from its elements according to the following equation. So this equation right here is already written for us, and we've checked both sides, and you can see that it's already balanced. But if it wasn't, you'd have to balance it to do this correctly. So the first thing that it tells us here to do in A is to identify the limiting and excess reactant if 18 grams of magnesium reacts with 20 grams of oxygen. So here's how we solve this. Now, if you were to go online and look, there are several different ways in which this can be solved. And I'm just going to, for the sake of time, pick the way that is, in my opinion, the best way, because it helps answer some other questions for us down here, and it gives us some good practice with conversions. There are some quicker ways for determining the limiting reactant and the excess reactant, but this is just the way I prefer to do it. Kind of is a nice way to get another answer later on here in B. So what we're going to do is we're going to take the mass, in this case, because we've been given the mass, of both of our reactants, and we're going to convert them to a mass of product. So we have 18 grams of magnesium, and we're going to convert this to a mass of product. So the first thing we have to do, if we're going to kind of bridge the gap between our magnesium and our product magnesium oxide, is we have to get to moles, because our balanced equation, of course, is in mole ratios. Let's say 2 to 2 mole ratio. So we need to get to moles of magnesium. So we'll need a molar mass for magnesium. We'll just come over here and we'll see the molar mass for magnesium is 24.31 when rounded to the hundredths place. And so we'll put that down here, 24.31 to 1 mole of magnesium. Now we're ready for the next step. We're going to go from moles of magnesium to moles of our product, magnesium oxide. Let's finish, get a little up there. All right, now let's look at the coefficients. We have 2 and 2. So 2 moles of magnesium are used to produce 2 moles of magnesium oxide. And we're able to cross these off as we go. Now finally, last step, we need grams of magnesium oxide, because you could stop at moles in both of these scenarios and kind of see which one you have more or less of, but because part B up here asks us to calculate the mass of magnesium oxide formed, we'll just go ahead and convert to grams of magnesium oxide, because it's going to go ahead and answer part B for us. So moles of MgO, magnesium oxide. 1 mole of magnesium oxide contains a certain number of grams of magnesium oxide. So we go over to the periodic table. We find magnesium and oxygen. So magnesium 24.31. Ooh, I messed that up. 24.31. Let's get a better color we can see. So molar mass for magnesium is 24.31, came from here. And the molar mass of 1 oxygen is 16. So we add 16 to this. And the molar mass of magnesium oxide is 40.31. So we're going to come back over here and put 40.31 in our blank. So we have 40.31 grams of magnesium oxide per 1 mole. So now we're ready to do the math here. Now, kind of something you can do ahead of time here to sort of simplify this is this 2 over 2 here can be reduced back down to 1 over 1, and so it actually kind of makes our math a little more convenient. What we have is 18 times 40.30. So let's write that back down here again. 18 times 40.31 divided by 24.31. So let's get our calculator out. We have, let's turn it on. Oops, there we go. 18 times 40.31, and then all of that divided by 24.31. And we get 29.84. And of course, 18 here, 18.00, has 4 significant figures as well as these other numbers. So our final answer will also have 4 significant figures. 29.846 will round to 29.85. So our answer is 29.85 grams of magnesium oxide. And that actually may be out of the frame there. We'll move this over just a bit. All right, so let's get rid of this down here. Give us some room to do this next problem. All right, we got rid of that. And I'm going to move this down just a little to give us some more room. And so the next thing that we're going to do here is that we're going to go from, pull this up a bit, we're going to go from 20 grams of oxygen to a mass of magnesium oxide. So we're going to do that again here. So we have 20 grams of oxygen, and we're going to go to a mass of our product. So this is an oxygen molecule, so there are 2 oxygens, and if you check your periodic table, each oxygen is 16, so 2 of them is 32. The molar mass of this oxygen here is 32 grams per 1 mole of oxygen. Now we're going to go from oxygen to our product, magnesium oxide. So our balanced equation tells us that 1 mole of oxygen, here, 1 mole of oxygen, will produce 2 moles of magnesium oxide. 2 moles of magnesium oxide. And the last thing we want to do here is, again, we're just going to do the same thing that we did here, down here, because all we want to do is go from moles of magnesium oxide to mass. And so we can kind of just sort of copy that step down here. We want to go from moles of magnesium oxide to mass of magnesium oxide, 40.31 grams of magnesium oxide. Okay, so let's grab our calculator and do our math here. So we have 20, let's see, that's going to be out of the frame there, isn't it? All right, we're going to have 20 times 2 times 40.31 divided by 32. So that's what we'll do here. We have 20 times 2, which we could have done that in our head, 40, times, let's see here, 40.31 divided by 32. And that leaves us with 50.38. And with the 4 significant figures here, we can see that we would round this to 50.39. The 7 will bump the 8 up to a 9. So 50.39 grams of magnesium oxide. All right, so we have 2 answers here. So what do these 2 answers mean? What do they do for us? Well, what we've essentially done here is we've said, okay, if we have 18 grams of magnesium and we use all of it, how much product can we make? We can make 29.85 grams. And if we have 20 grams of oxygen and we use all of it, how much product can we make? 50.39 grams. So the limiting reactant is whichever reactant produces the least amount of product. And in this case would be 29.85 grams of magnesium oxide. So our limiting reactant is the magnesium and our excess reactant is the oxygen. So for part A, magnesium is the limiting reactant, and oxygen is the reactant that is in excess. Also, by doing this method, this answer right here is actually the answer to B. What is the mass of magnesium oxide formed? So, or at least the first part of it. So the mass of magnesium oxide formed is 29.85 grams of magnesium oxide. This calculation right here isn't useful to us anymore because we now know that this is how much you would get with the excess reactant. So it's nothing that we need. So what we can do here is we can go ahead and erase this because we're not going to need it. And we'll be able to move on and do some more of our problems here. So I'm going to erase the math part here, but I'm going to leave the mass of our product up here so we can use it. Now let's go on to the second part of part B. It says, calculate the mass of the excess reactant remaining. And here, this is going to be actually pretty easy because what we know from the law of conservation of mass is that however much grams of reactants, whatever mass of reactants we have, that must equal the mass of our products and whatever else may be left over. And so we already know that our product is 29. This is our product. Our product is 29.85 grams. And we know that our reactants were 18 grams of magnesium plus 20 grams of oxygen for a total of 38 grams of reactants. 38 grams of reactants. So 29.85 grams of product, the difference between these two numbers, 38 and 29.85, is the mass of the excess reactant left over. Because of this 29.85 grams, 18 of it is magnesium. Because remember, magnesium was limiting, so all of it has been used up. And whatever is left over is how much of the 20 grams of oxygen has been used. So we can take 38 and we can subtract from 38 the mass of the product, 29.85 grams. And we'll grab our calculator just to be sure here. We have 38 minus 29.85 grams. And that gives us 8.15. And that's our answer for the mass of the excess reactant remaining. We have, lost it, 8.15 grams. Now, you may or may not be asked this next part. Oftentimes, that's where these problems typically end. But I'm going to include a couple other things here just in case. So sometimes they'll go on to ask you, well, how much of the limiting reactant, which we now know is magnesium, would you need to add to use up the rest of the excess reactant, which is 8.15 grams? And so at first that seems like it would be a little confusing, but really it's quite easy. What you're going to do is just simply convert 8.15 grams, which is the amount of excess remaining, and you're going to convert that to a mass of magnesium, and that will be the mass of magnesium that you would have to add to use the rest of it up. And so that's what we'll do here. So we have 8.15 grams of our excess reactant, which is oxygen, and we're just going to convert that to a mass of magnesium. So there are 32 grams of oxygen in 1 mole of oxygen. Our balanced equation tells us that 1 mole of oxygen reacts with 2 moles of magnesium. So that's what we'll put here. 1 mole of oxygen will react with 2 moles of magnesium. But remember, on C it asks for the mass of limiting, so the last step here is just another molar mass, mole to mass conversion. And so 1 mole of magnesium is 24.31 grams. Just to double check that, we'll go over to our periodic table and we'll see that the molar mass rounded to the hundredths place is 24.31 grams. So we'll grab our calculator here and we'll do 8.15 times 2 times 24.31 divided by 32. So, round it to the correct number of significant figures, which in this case we started with 3, so we should round our answer to 3. We would round this to 12.4. So we will need approximately 12.4 grams of magnesium to react with the remaining amount of oxygen, 8.15 grams of oxygen. And then the last question that it asks here is just a percent question. It says calculate the percent yield if a group of students in a lab recovers 9.5 grams of magnesium oxide. So all this is just a part over the whole. All a percent is, remember, is just part over the whole. So what we're saying is that obviously nobody's perfect. We couldn't go into a lab and get exactly 29.85 grams of magnesium oxide. We're not going to be great at getting 100% of this. And so percent yield is a good way to kind of tell us kind of how good we've done. So this right here is called a theoretical yield. That's what it means, is saying theoretically that's how much we could get if we could do this to 100% accuracy. But obviously we can't. So this is just giving us sort of a scenario. 9.5 is just made up by the person who wrote this question. So we have 9.5 grams of magnesium. This is called an experimental yield. So it's what we get when performing the experiment. Oop, one too many L's. Experimental yield. So the way that you calculate a percent yield is it's just experimental divided by theoretical, and then of course times 100, which just scales it up to 100. So that's what we'll do here. We have the experimental yield, 9.50 grams of magnesium oxide, divided by the theoretical yield, 29.85 grams, and then we'll multiply that by 100. Or if you don't like multiplying by 100, you can just move the decimal over twice. So let's go over to our calculator. We have 9.5 divided by 29.85, and then times 100. But again, that's just going to move that decimal over twice to 31.8, but we'll go ahead and do it anyways just to be thorough. And we get, there you have it, 31, oops, where'd it go? Oh, here we go, 31.8% yield.